Okay, we'll get started. Sorry about that. So now, before the break, we introduced the Gaussian mixture model. So we have k Gaussians. Pj of x is Gaussian with mean mu j and covariance sigma j. And we showed that, or at least I told you that the formula here is 1 by 2 pi raised to d by 2 square root of the determinant of sigma exp minus x minus mu j, sigma j inverse x minus mu j divided by 2. Now the Gaussian mixture model is p hat of x, which is some weighted sum of pj of x.
Can you make it full screen
again? Okay? And the intuition here is that the weights intuitively denote the probability of selecting the jth Gaussian. So we want to sample a data point, and we do it in two steps. One is that we select one of those k Gaussians. The jth Gaussian is selected with probability Wj. So this is a first level of randomization. Once we select that Gaussian, we then sample from that Gaussian. So the picture to keep in mind here is that imagine that you have two Gaussian densities like this. This is Gaussian with mean mu1 and covariance sigma 1. This is Gaussian with mean mu2 and variance sigma 2. And let's say W1 is 1/4, W2 is 3/4. Then if I want to sample a new data point, I will select this cluster with probability 1/4. That's what W1 signifies. Once I select that, I will then use this particular density function to sample it. So if depending on the mean and the covariance, this might be the cluster. So this is basically the ellipse where the PDF is a constant. And typically you show the first standard deviation for the ellipse. So the data points which are sampled using this cluster might be like this. This is the second Gaussian, and so here because it has a higher weight, there might be more data points here. This is selected more often than this. Once I select one of the Gaussians, then I don't make a deterministic choice of the output. I still use the PDF of the Gaussian for sampling. But because of the way this density function is shaped, I will have some point belonging to a cluster here if I select this Gaussian. And if I select this Gaussian, then the points will be in this cluster. So that's how the output will come out to be. First, I select whether I want to use this Gaussian or this Gaussian. Once I make that choice, then I use this density function to do the actual sampling. And mathematically, that two-step operation is represented by this formula, the formula of a Gaussian mixture model. Any questions about this? Because we'll be extensively using this in the next part of in the lecture that we just do. Any questions about the notation, the interpretation? This is the last recap of the Gaussian mixture model. Then we will build up on this when we introduce the EM algorithm. Hopefully everyone is okay. So now the question is that we are given our data set. We are given n points in RD, and we are given k, the number of Gaussians. And our goal is to find Wj, the weights, the means, and the covariance. So these are our model parameters, right? And we want to find this, that best, so such that p hat of x, which is the summation of Wj, x, mu j, sigma j. This is the weighted sum of the Gaussians that best fit the data set D, the endpoints that we have. Okay. So for each choice of Wj, mu j, and sigma j, I will have some density function, p hat of x. Once I select these parameters, these are my model parameters. Once I select them, I get a p hat of x. Okay. My goal is to select these parameters that best fit the data set. All I have access to is my training set. I have these endpoints. And I want to choose the parameters that are the best fit for the data set. This is the question we are interested in. Okay? Any idea what the best fit should be? What should be the, how should we define, what's the natural definition for the best fit?
Minimize the error function.
Okay, what error function that should be used here? The maximum likelihood. Okay, so the idea is that for each choice of these parameters, you will have a density function. This density function will assign a certain probability to x1, it will be p hat of x1. It will assign a probability p hat of x2 to x2 and so on. Now you want to choose you want to find p hat of x that maximizes the probability assigned to this data set. That is all you have. You just have access to these endpoints, right? Everything else is part of the model. The fact that you're assuming a Gaussian mixture model, assuming what mu j, sigma j, and wj are, they're all part of the model. You want to select this model parameters that best explains the data you have already observed. Or in other words, that is, by best fit, we mean the maximum likelihood solution. So in other words, we want to find omega that maximizes, so let's put omega as a subscript here because the model parameters determine this omega is just wj's, mu j's, and sigma j's. So you put it there. So that maximizes p hat omega of x1, x2 up to xn, which is the product of n going from 1 to capital N, p hat omega of xn. So this is our goal. We want to maximize the probability assigned to the data set that we have actually seen. And since we assume all the data points are sample IID, which is a natural assumption here, then that means that we are going to maximize the product of the probabilities assigned to the endpoints. Or in other words, we want to minimize minus log p hat omega of x1, x2 up to xn. Instead of maximizing this quantity, it is always convenient to take the log when you deal with probabilities. So take log on both sides, so this becomes a summation and this looks like an error function. And we minimize, because log is monotonically increasing, maximizing this is equivalent to maximizing log of p hat of omega, or equivalently minimizing minus log p hat of omega, because we want to define an error function. So let me write that. So we want to minimize summation of n going from 1 to capital N minus log p hat omega of xn. Okay. Now we know what p hat omega of xn is. Who can tell me what the value of this is? Anyone tell? Suppose I am given my model parameters. What is p hat omega of xn? Yeah? It's not quite the weights. Weights is basically the probability assigned for the jth Gaussian. So Wj is simply the probability, if you go back to this figure here, whether I select this cluster or this cluster. It's not the density of xn. What is p hat of xn? How do I compute this quantity? Anyone? Yeah? Think it's obvious? It is actually, I was hoping it's obvious, not a trick question. Yeah, well, p hat of x is defined here, right? So you just evaluate this at xn. That's what it will be. Basically, if you go back to one of our earlier examples, if you go back to the Gaussian mixture model, here we had k equals 3. 3 Gaussians. This was weighted by 1/4. This was weighted by half. This was weighted by 1/4. So if you want to, if let's say your data point is here, this is your xn, and you want to understand what's the probability assigned to this point, it's basically p hat evaluated at that point, right? And p hat is just basically a weighted sum of this, which is what this formula was doing. So it's just this formula when x is evaluated at xn. So this you can write down. So we want to minimize the summation of n going from 1 to n minus log summation of j going from 1 to k wj times the Gaussian xn with mean mu j and covariance sigma j. That's it, right? That's what it is. This is an analytic formula we have for p hat of x. All we have to do is evaluate it at the data point of interest, xn. So just replace x by xn in that function and you will get a value. Is this clear? This is a key step. Like this tells you what a Gaussian mixture model is, how it's assigning probabilities to different data points, what's the role of different Gaussians, and so on. There are questions you should ask now. So now the point is, this is a well-defined loss function, right? You give me wj, mu j, sigma j, and so this depends on wj, mu j, sigma j, and the location of the points x1, x2 up to xn, right? So I want to minimize this. So this is my error. This is En of omega, right? I can write En of omega as a sum of n going from 1 to n times En of omega, where En of omega is just the loss on one point. This is a loss on training point xn, and I can always minimize 1 over n. That's just a constant, normalization constant. So En of omega is simply the average loss that I have for my model with respect to the endpoints. And I want to minimize this. And I want to select omega star to be argmin of En of omega, right? This is again, now I have a standard machine learning framework. I have my model parameters, which is this mixture of Gaussians. I have my loss function, which is additive across the n training points. And I want to minimize it with respect to my model parameters. So what should I do next? How do I find the optimal omega? What comes next? Let's say you formulated the problem. Now you want to implement it. You are given n training points. Maybe each point is in 3 dimensions. You have 100 points, right, which are placed. You know that k is 3. You know 3 Gaussians that you want to use. How would you end up finding your model parameters? Yeah? You do gradient descent. That's it, right? And whenever you have a formulation like this, the first thing to do is like, that's it. Now you have essentially solved the problem numerically. You take the gradients and do gradient descent. It may not be globally optimum, as we saw in the case of neural networks. This is not a convex function by any means, but you will get a local optimum. So in a sense, the problem is essentially solved at this stage, because now you can feed it into a gradient descent optimizer and it will minimize whatever parameters you're interested in. There is one catch, however. This is not that straightforward. Can anyone tell me why gradient descent is not that straightforward here? What would be some issues you would have if you do straightforward gradient descent? Yeah? This is a constraint minimization problem. One constraint is that Wj's are all positive. They have to add up to 1. So this is not a simple unconstrained optimization problem. Another issue is the covariance matrices. This is a bigger constraint. You're optimizing over matrices here, not over scalars. And these matrices are not arbitrary. They are symmetric, right? Because sigma ij and sigma ji should be the same. And they are positive. They all, as I told you before, their eigenvectors are all, eigenvalues are all non-negative. This is also known. So it's not only they are symmetric, they are also what are called positive semi-definite. They have a very special structure to it. So if you just took the gradient with respect to all the variables and took a step in that direction, chances are you will violate all these constraints. Okay? Chances are that W's will not add up to 1. The matrices will no longer be symmetric or positive semi-definite and so on. There will be issues. Now these are not impossible things. You can actually circumvent all these difficulties. There are extensions of gradient descent called projected gradient descent, where you force the variables to always stay positive and sum up to 1 by projecting it appropriately with the right constraints. So there are extensions of this. It's not like this is because you have these limitations, you cannot do gradient descent. You can, but it's going to be a bit more complicated. Each step will be expensive because of these constraints. Secondly, the function is not very nice. It's log of the sum over k terms. So when you take the derivatives, the gradients are going to be difficult to compute because the function itself is not very nice. It will be quite complicated. It have a log and then you have a summation inside the log. Even computing gradients is not that easy. It's going to be difficult computationally. Again, not impossible. In principle, you can do it, but it's not ideal. So because of these reasons, there is another algorithm that is quite popular here, which is the expectation maximization algorithm, or the EM algorithm. And the idea is that we want to numerically minimize this expression, but not using gradient descent, using a different algorithm called the expectation maximization algorithm. Right? So this is in some sense the generalization of the k-means algorithm that we saw last week. there will be two sub-problems, both of which are easy to solve. And if we iterate between those two, we will then converge to a global optimum. So it's the same principle. So we'll introduce two sub-problems, both of which are not too difficult. They can be in fact solved exactly. And then we will iterate between the two that will solve the original problem. So to do that, so we will define auxiliary variables, just like we did in the k-means thing. So we'll define B1, B2 up to Bk, which are all subsets of the original training set D. So we're going to partition our data points into k clusters. So here Bi is the set of elements in D sampled from the density Pi of x, which is Gaussian with mean mu I and covariance sigma I. So we are going to assume, remember that switching diagram where we had three branches? We'll assume that B1 corresponds to those points in D which were sampled from the first branch. B2 corresponds to those points which were sampled from the second branch. And B3 corresponds to those points sampled from the third branch. Okay? So here all the BIs are again just like before. They are all disjoint, so there is no overlap. And the union of BIs is our entire set D.